Alright, Chapter 5, Thermal Capacity of Freight Car Wheels. Alright, the report number of FRA ORD 7820, number 2, Brake System Design, Optimization, number 2, Volume 2, Supplemental Data, and we're on 5. Thermal capacity of freight car wheels. Introduction. Thermal capacity of freight car wheels represent the major design criteria that has been taken into account with the air brake system design. Each of the design braking level must be limited with thermal capacity not exceed the unit with the normal abnormal operating conditioning of the brake and effort must be achieved with the augmenting tread braking with the other forms of the braking. There are various forms of the research with several attempts made with the especially within the past 20 years to determine the actual thermal capacity of the freight car wheel. Typically for the foundation of North America, the research include with the experimental theoretical approaches. In particular, much of the use has been made with the dynamometers to perform various kinds of experiments to investigate the thermal capacity of the freight car wheels. The purpose of this section is summarize to discover the most significant portion of the research activities present with the collective assessment of the thermal capacity of the freight car wheels. Parameters is consider because of the many variations found with the train brake, the equipment of the operation of the effect of the wheel thermal with the capacity of the evaluated with respect with many of the parameters that can affect. These parameters include the following: cycle versus the drag brake, drag braking, B wheel geometry, size and shape, wheel material and heat and treatment, worn versus new wheels, brake shoe material and shoe alignment, other consideration. Each of these topics is discussed in the following items of the research after the performance of the recent years. Cycle versus drag braking. The thermal capacity of the wheel is dependent on the type of the operation of the wheel. Extreme the terms of the surface of the cycle braking, either the engine with the control of the train slack, action operating along train with the undoubtedly the train terrain, although brake level to either the type of the braking, also called stretch braking, are normally not large. These wheels are exposed to the alternate circle of the heating and the cooling. Another form of the braking limit can be considered the cycle braking and is full surface emergency brake application when the engine is banned to produce a large chain with the train speed. For example, the 50 mile an hour to a stop, again with the wheel travel, the temperature, they increase with a high value with a short period of time, and then drops back with the ambient level at a rate determined with the ambient condition. The original with the other type of the freight train brake operation referred to with the drag braking, normally associated with the steady brake application over a long period of time. Typical occur with the train is being operated down long steep grade where train brakes are applied with the balanced gravitational force of the grade. Save thermal load with the in-research project sponsored with the Griffin Wheel Company. Save thermal load with the defined with the thermal load which does not produce an elastic deformation in the wheel. An elastic deformation produced in surface because of the braking of the manifestation residual stress, and if the wheel can be caused by a large variation of temperature between the wheel tread surface and other portion of the wheel. The variation of the temperature referred to a thermal gradient. They believe the sum of the investigators to be somewhat sufficient in causing wheel residual stress, then equivalent to the even higher with the tread temperature for the sustained with a long period of time. In other words, thermal shock of the fact with the psychological braking considered some of the research to the more is effective with the wheel than slow, rapid, uniform high temperature brake application followed by a slow cooling process. Place the thermal capacity of the wheels perspective with the respect of the cycle drag brake equipment. Application of the brake level to both the type of the application must be known. For example, a high level of the drag braking could theoretically exist in which the wheel temperature could reach the destructive level, assuming the brake shoe would not disintegrate, the wood would fail, the amount of the cycling brake would not be a factor. Or a recent testimony. The recent testimony conducted at the University of Illinois several the type of the wheel braking level of the cycle with investigated the wheel diameter with the residual strength of the measure after subjecting the wheel to various brake level of the measuring with the opening of the solve of the cuts made with the wheel rim after testing the result of these tests shown in figure 1. Opening 10 inches and squared depth of the cut in inches 2, 4, 6, and 8, and then you have A through X through B, C, D, E, F, G, H, and I line. Alright, the research made the following conclusions concerning the results shown in figure 5.1. Started with giving the wheel design, heat treatment, that appearing with the more of the survey of the application for the grade of the opening of the wheel, opening perform radial saw cut. The result with the imply with the most severe load with the series of the 100 horsepower to test with the first 15 miles an hour, 15 minutes. Type of the test with the was virtually consumed with the newly composition sheet with the one type of the possibly extreme with the surface with the truck brake with a substantial more serve brake cycle with the furry surface of the difficult with the imagine of the wheel subject with the thermal low fraction of the radial saw cut in progress toward the rim and none of the other wheel with the fracture of the solid for the fortunately the dab with the rather well with the define with the point with the first present would seem with the thermal load with the producing substantial less saw cut opening with the wheel with the fracture upon sawing should be reasonable safe. It should be noted that above the mentioned case with 100 horsepower 15 minutes the wheel did not fracture until the saw cut was made with the tread temperature for the reach of 1146 degrees Fahrenheit and new composition brake shoe was consumed during the test. However, this wheel with the combined physical load with the repeated thermal cycling of the actual train operation could be surmised. 522 wheel geometry, size, and shape. The wheels have the diameter of the shape of the cross section, additional factor of the effective of the wheel with the thermal capacity. Both of these factors discussed below. Wheel size and reach of search of the performed by the Westinghouse air brake system. Even the full scale of the dual wheel diameter dynamometer investigation was made with this thread. The temperature that would produce the various kinds of the wheel was given with a horsepower dissipation during the braking. The following diameter type of the Class B wrought steel with the wheel with the test in both of the new tread with the worn tread condition 40-inch multi-wear, 36-inch multi-wear, 32-inch multi-wear, 36 one-wear, 28-inch multi-wear, and 20-inch one-air. Result of the test presented in Figure 5.2 with a new wheel with the max wheel tread in temperatures of Fahrenheit. The range from 0 to 200 to 1,000. New wheels from 28, 33, 36, and 40 inches. Alright, A. The conclusion of the test results are solved with A. As the brake horsepower per wheel will increase with the temperature rise, with the given the wheel will increase with the same length. With B, the as nominal wheel diameter decrease with the temperature rise with the wheel to increase. Then C, with the actual wheel the diameter due to the wear is decreased with the temperature rise with the wheel with the increase with the approximate range of the temperature through the width of the chain with the curve of the verse of the nominal wheel diameter approximately in a straight line. Maximum wheel thread with the temperature of the wheels again stand without a problem to determine the allowable brake force with the per wheel. Therefore, the grade braking operation wheel shape of the effective of the thermal stress of the produce of the tread braking combined with the physical stress of the produced by vertical lateral loading have been investigated. Performing analytical stress analysis of this research is performed in part to explain what the difference of the wheel plate with the failure of the 28-inch wheel with the straight curves cross section using two-dimensional finite the difference of finite element mathematical method of calculating octahedral head shear stress of 28-inch straight plate and curved plate CB28 and wheels will be evaluated and serve the load application for the vertical lateral wheel loads and flange throat in combination with emergency brake application for the load applications are shown schematically in Figure 5.3. I show the 108 the rail brake and shoe plane, wheel rail load plane. Coordinate system load application reference plane to analysis wheel stress. Surface loads applied where it's filed with car wheel rail. Contact loading vertical 40,100 pounds. Lateral 20,000 pounds. Shred braking load brake shoe force 6,200 pounds. Tractive force 72 pounds. 720 pounds. Thermal load, particular thermal load applied with the wheel corresponding with the temperature distribution wheel with a 55 second with the brake application with the tread surface the temperature for the air at maximum of the temperature field with the braking with the intervals shown Figure 5.4 and 5.5. 5.4 straight plane wheel thermal loading, and then curved plate wheel thermal loading. Maximum octahedral shear stress calculated where to describe what the authors are followed. Maximum octahedral shear stress produced adjacent front with a hub fillet over the straight plate with the wheel with the load applicant was significantly higher with the tread generally rated only by the rolling loads, vertical, lateral wheel loads. This maximum stress occurred with approximately 45-degree wheel rotation. Diminished with the wheel rotate with a 180-degree position. Maximum octahedral stress intensity of 13,500 pounds. Near the back of the rim fillet with a curve at 45-degree angle with a wheel rotation diminished with wheel travel approximately approaches 180 degrees. The author noted with the previous work was found with a mechanical wheel reel contact loads comparable to those found surface most efficient and induced plate failure with either straight plate with a curved plate or 28-inch wheel. The author continued, however, the introduction of thermomechanical loads produced with the emergency braking combined with the mechanical rolling loads produced with a considerable higher octahedral shear stress level in plate section of the B28's design compared to the CB28 design. This would be indicated that the B28-inch wheel will develop with a greater number of the plate failures for the CB28 depending on the number of the braking cycles included during normal surface operation. Since both wheels are designed and subjected to essential with the same surface condition, plate failures have occurred, and only the B28 design is most likely to travel within the CB28 plate are below threshold necessary to initiate fatigue failure. Alright, wheel types. There are several types of wheels used within the railroad industry today. They are types vary according to material. The method of manufacture design differences. Both wrought steel with the cast steel wheel are approved to replace with the new car construction. Cast iron wheels were prohibited to interchange service after January 1st, 1970. Cast steel wheels, cast steel wheels are made in one wear, two wear, multiple wear designs furnished with its various heat treated classes, carbon leveled according to the AR specifications. Cast steel wheels are permitted to cool when the molds of completed solidification wheels are removed with the mold, cooled under controlled conditions either before and after the center of the hub to remove the rough bore. All cast steel wheels receive a heat treatment to produce the desired metallurgic change that provide favorable stress distribution in the wheel. Except the one class of the cast wheel steel is class U. All cast steel wheels receive quenching treatment on the tread surface to produce the hardness required by AR specification. Class A, B, C wheels vary in their carbon content and hardness. 5232 wheels, wrought steel wheels. Wrought steel wheels are made with except for the hammering squeezing operation of the hot steel blocks. After finally shaping the wheel with the control cold, wrought steel wheels are often heat treated after initial cooling, either fully or room quench only. Perfectly heat treatment is effective further than modification wheel metallurgy, strengthening and hardening the wheel. 5233 AR specification governing wheel manufacturer. The AR specification defines the chemical requirements of the wheel, carbon content, impurities, physical requirements of the hardness, various points on the wheel surface, the finish, and the requirement of the wheel classification, incorporating the requirements are shown in table 5.1. Alright, so the class U with the untreated with a minimum of 0.65, 0.8 carbon content, generally surface where untreated wheels are satisfactory. UI untreated 0.95 minimum carbon content. 1.2 high-speed surface braking condition, but moderate wear loads. A treated 0.47 to 0.57, and then the same recommended use. B treated 0.57 to 0.67 high-speed surface with moderate braking conditions, heavier than wheel loads. C treated 0.67 to 0.77 surface with light brake conditions, high wheel loaded surface with heavier braking conditions where off-tread brakings are employed. And in L treated, you have your maximum carbon content 0.47 and your recommended conditions high speed passenger transit. Class A wheels, low carbon range, are most resistant to thermal cracking. Class C wheels are more subject to thermal cracking but are improved wheel or permanent properties under heavy loads. Class B wheels represent the compromise between Class A and Class C wheels. 524 worn versus new wheels. The amount of wheel wear is effective with the thermal capacity of the wheels in general. With the more worn wheels, the higher the tread temperature, the lower the thermal capacity is given the level of the braking. Especially true with the smaller diameter wheels. In tests performed at the Westing Air Brake Company, the wheels subject with the constant brake horsepower levels for long periods of time, up to 60 minutes. Figure 5.6 compared with the temperature versus time curve of the new wheels worn. Wheels you can do these tests, and that shows figure 5.6 shows the time in minutes, wheel tread and temperatures. Maximum tread temperature reached 40 bhps as approximately 600 degrees Fahrenheit. New wheel temperature new wheel versus approximately 720 degrees Fahrenheit for the warm wheel, increased to 120 degrees Fahrenheit. For the warm wheel compared to the new wheel, the high temperature effect of the warm wheel even more than apparent small diameter wheels. This is shown in figure 5.7. 5.7 shows the comparison tread temperature versus the new and worn 28-inch multi-wear wheels. Maximum tread temperature 60 minutes with the BHP with the 20-inch wheel with approximately 760 horsepower, 764 degrees Fahrenheit versus approximately 900 degrees Fahrenheit for the warm wheel. Increased 190 degrees Fahrenheit for the warm wheel compared to the new wheel. Closely related amount of wheel wear and effective with the maximum road tread temperature wear category multi-wear versus warm wear of the wheel effectively can be seen with the figure 5.8 with the summary of the test results showing maximum temperatures reached each wear category wheels tested. 5.8 shows the summary of the wheel temperature test results comparison wheel categories. 1. In general, one-wear wheel temperatures are higher multi-wear temperature when wheels are new. For worn wheels, the difference between one-wear and multi-wear temperatures become almost negligible. Wheel tread temperature increases inversely the wheel diameter directly with the amount of wheel wear. When wheels are new, the temperature side of the relationship with the significant multi-wear wheels. However, when the wheels become worn and effective as needed, Alright, 5.25, brake shoe material and alignment. Brake shoe material. Up until 1969, almost all wheel thermal capacity tests performed under the cast iron brake shoe held in collapse arrangement. 1969, a report published by the ASME documented the testing Class C wheel thermal capacity used composition Cobra brake shoe. The report briefly contained the earlier tests performed. University of Illinois' 1950 test where stop tests stipulated with a rapid deceleration rate of 115 miles an hour. And these tests stipulated with the wheel load of 20,000 pounds was used with the conjunction brake shoe force, 20,000 pounds on each two cast iron brake shoes held in collapse arrangement. The braking duty of the representative of the total kinetic energy of the 9 million foot-pounds per stop. The result of these tests, as summarized by the authors, are of 5 classes C are wheels, Class C rim treated, which were tested in the manner they are developed in thermal cracks after only one stop. The remaining 2 wheels developed cracks after 5 stops and 7 stops, respectively. Following serious stress tests performed with documented wards, this code Dewey, the test stipulated that the stops within 31,000 pounds wheel load instead of 20,000 pound wheel load, a pound load above the 13 test. Result of the test were as follows. These studies are extremely valuable that it resulted in a much better understanding of the mechanism theories of the formation of the defects developing in wheels and resulting in the braking. Is noteworthy extract with the particular result of these tests report results obtained in 1950 University of Illinois have determined that stops required to produce thermal cracking CR wheels was one stopped. In 1968, another test series was conducted with the purpose of obtaining the direct comparison wheel thermal capacity of the wheels baked in single-flange Cobra composition brake shoe, wheel braked in cast iron shoe for the second purpose for the verified previous test result. Cast metal shoe, there are these test dynamometer stops, particularly oriented towards metro liner braking condition test parameters shown figure 5, table 5.2. 5.2 test parameters, cast iron Cobra brake shoes comparison. Show the parameters, wheel steel, number of brake shoe, the Cobra brake shoes, every wheel location, equivalent wheel load, total simulated car weight, brake arrangement, net shoe force per wheel, initial speed, kinetic energy per stop, foot-pounds, average stop distance, average stop rate, or stop time, average work rate per stop, foot-pounds per second, average maximum wheel tread temperature, average retardation rate, total braking work done on wheels, foot-pounds. The test result was summarized with the authors followed after approximately 20 emergency stops were completed. Each wheel with the number 8925 metal brake shoes when they developed hairline, skin deep thermal crack. The abundance of these thermal cracks increased with the successive stop. Each successive stop 1370 through 87 the stops completed on wheel number 1079-3 with a flange Cobra brake shoe. Dynometer was being accelerated for the 37th stop on the wheel number 8925. Sharp ping was heard instead of the proceeding with the emergency stop. The machine was stopped without brakes on the wheel in question, and an examination revealed severe thermal crack extending almost across complete width of the tread of the wheel. The number 8925 of the test discontinued at this point. Braking duty dissipating in 9 million foot-pounds, kinetic energy at a rate over 137,000 foot-pounds per second with a cast iron brake shoe with 140,000 foot-pounds per second with a Cobra brake shoe and serve with any practical service stand with exercises previously recommended limited 125,000 pounds per second. Another paper presented at the Air Brake Association annual meeting further test results were documented in particular following conclusion. The initiation of thermal cracks and dynometer testing well documented with the other offered strong proof of the wheel real load and necessary component with the thermal cracking formation virtually impossible for the induced thermal cracking using composition produced brake shoe full scale dynometer no problem inducing thermal cracks cast iron shoes under these circumstances. See, thermal cracks once formed can be propagated dynometer using either type of the brake shoe. Second conclusion stated above the explained by the examining treating heating pattern characteristics of the cast iron composition brake shoes. The characteristics are compared in the following page, figure 5.9. Figure 5.9 show the comparison of average maximum thread temperature cast iron versus composition breakthrough. Or the maximum tread temperature for the composition shoe, the wheel more equal to average tread and temperature for the equivalent wheel braked by cast iron brake shoe at 110 brake horsepower dissipated rate difference maximum or average temperature can be between 500% and the temperature differential one of the primary of the thermal damage. 5252 brake shoe alignment. The brake shoe misalignment may also known affect the thermal capacity of the wheels given the level of the brake shoe force. Berg and Carissa made the following statement in concern of the brake shoe alignment, page 15. Not enough emphasis can be placed on the importance of having the proper line braking, rigging, thereby conformed and further to experience localized heating of the differential effect of the performance of the wheel. British hypothesis put forward earlier suggested the rolling contact action between the wheel and rail produces the beneficial surface residual compressive stresses. Thermal crack, the claim cannot be even the brittle fracture for the penetrated this layer. Furthermore, the brake shoe must be allowed to wander over the front of the rim last thin issue with the thermal cracking area unprotected. The preceding rolling contact. It's for the same reason the British railroads have abandoned the use of the flange shoes except for the slow-speed vehicles. Other considerations. Several other considerations must be investigated, estimating wheel thermal capacities. They are briefly discussed in the following. Aerodynamic cooling. Most of the research performed investigated wheel thermal capacity did not include beneficial cooling effect that the wheels would receive the actual train operation, although some of the research of doing the position electrical fans circulating airs over the wheel being tested, none of the research result quantified effects of the cooling airflow. Closely related to aerodynamic cooling is ambient air temperature environmental through the train is being operated based upon experimental theoretical result found in research paper that assume the most favorable wheel temperature condition for the produced level braking application cycle made on a wheel operating with low ambient temperature. 5262 variation brake versus although the brake system design produced for the uniform brake level to all wheels over the car experience indicate that this is not always the case because of the binding rigging misapplied brake shoes. The other causes actual brake shoe force of the substantial form of the one wheel to another same car. This can cause higher than more normal wheel tread temperatures, one or more wheels within the train. Slid flat wheels. Slid flat wheels are a common problem of the present train brake system and the rail that freight train preserve the passing without at least one pair of slid flat wheels, 1 degree or another. Slid flat wheels can be caused on released handbrakes, misapplied brake shoes, malfunctioning slack adjuster exemptional, high braking brake pipe pressure settings, binding brake rigging, malfunctional controlling valve, probably many other causes regardless of the cause of the slid flat wheels. Sliding process itself is generally high localized wheel tread temperatures. Empty car temperature would conservatively correspond to the brake horsepower dissipation rate, approximately 100 brake horsepower pressure through the wheel. 5.3 Summary. Because of the process of the estimating wheel thermal capacity must take into account several variables discussed previously. Because of the individual research series performed to date typically include these few variables and given the test series, it's difficult to provide collective assessment of thermal capacity for freight car wheels subjective to tread braking. However, summary can be made with the concern of the nature of the braking technology operating practically can result return most beneficial for the braking while simultaneously maintaining safe thermal loading. These summaries are presented below. Are some of the research at the top of the brake shoe research shown that the combined position brake shoe produced with lower wheel temperature gradient, the equivalent horsepower dissipation rate of the procedure by cast iron shoe. That these two reasons have been put forward to explain these results. The tread temperature distribution across the tread of the axle variation with a more uniform composition brake shoe. The cast iron shoe tends to form rings and bands extremely high temperatures on the tread, which local hotspots. The more uniform temperature distribution produced with the composition brake shoe can lose a smaller temperature gradient in radial direction, lower wheel stresses. Furthermore, as stated as a result of one of the tests that had been virtually impossible to do for thermal crack, the wheel of the composition brake shoe with the full-scale diameter immediately have one crack in the form of some of the other means cracks probably gave with the composition shoe. There should be further noted that some of the tests of the dynamometer with the composition shoe in most cases were consumed before wheel thermal crack. Wheel diameter cross-sectional shape. The test result indicated large diameter wheel exhibit a low tread temperature for the given level of the braking with a small diameter wheel. New multi-wheel wheels tread temperature produced within 40-inch wheel with more than 25% lower than temperature produced in 28-inch wheel, although the effect was not a significant warm wheel with the theoretical analysis for the 28-inch wheel would indicate that with the combined physical thermal load with the curved plate in the 28-inch wheel exhibited with a substantial reduced wheel strength compared with the tray plate 28-inch wheel. The result of the substantiated with the fact that the wheel plate failure for the selected with the freight train operation occurred exclusively with the tray plate wheels. Type of the brake rigging to avoid extreme variation of the brake level of the individual wheels of the freight car. The brake rigging must be capable of providing uniform balanced brake shoe force for each wheel, but also important selection of the brake rigging provided with the proper brake shoe. Wheel metallurgy. Although metallurgic content of the wheels typically selected the base due to the under consideration particular shelling, spalling, wear of the characteristics from the standpoint of the wheel thermal capacity of the wheel of the low carbon content of the most resistant thermal cracking Alright, brake application cycle speed with a grade operation temperature shock with effect with demonstrated to be damaged for the wheels of the brake application on one large time period of the time. In operation should be managed with a cycle. Braking severe nature should not be required so that the descending grade temperature speed are limited to safe level of the horsepower dissipation. Safe energy dissipation rate of the purpose of the above determine they present favorable conditions to obtain freight car wheels due to the outbreak and untreaded braking techniques. Safe energy disposition rate freight car wheels with a tentative determined for 33-inch Class U wheels. 1975 research performed out of the University of Illinois. Spun Griffin Wheel Company tentative of safe energy dissipation for versus time curve shown in Figure 511 should be noted that the result would include physical mechanical wheel loadings that would be experienced in services. Shows brake power per horsepower on wheel, the net temperature forces in wheels, gross retarding forces in wheels, and the grade percent. Alright, show the safe energy disposition rate, tentative energy disposition, horse versus time in minutes. Alright, your tentative safe energy disposition rate composition system tentatively approaches 40 brake horsepower level at the time, being substantial greater than 40 brake horsepower for shorter time periods. Various discussion research brake system professionals generally reveal the curve presented with Figure 511 corresponding conservative, especially true guidelines presented previously are followed. Then it goes into Appendix A, and that was the completion of the reading of the Brake System Design Optimization Volume 2 Supplemental Data Report number FRA ORD 7822.